This is day one of what most likely will be our last topic for the year. We may finish this up slightly before finals if we end up having them, yet to be determined at the time of making this video anyway. If we do get to another topic, it'll be something that we won't be able to do a full-fledged unit on. It'll just be lightly touching on it. Anyway, getting started here. Today we're going to start talking about limits. So what is a limit? Right, in simple terms, a limit tells us the y value that a function approaches as the function's x value gets closer and closer to some number. We will formalize and flesh out this description in more detail as we work through the unit. So it's not a very mathematical definition we provided, but it's good enough to get us started with what we need to be doing. The idea of a limit is the basis of all calculus. Limits are typically the main focus of Chapter 1 in most introductory calculus texts. Our approach in pre-calculus will not be as rigorous as you would typically experience in a calculus class. The goal is not to replace Calculus Chapter 1, but rather to prepare you for it. We will be addressing an overview of basic concepts of limits with some basic strategies to evaluate limits. Limits can be examined for any x values, but tend to focus on values where something interesting is happening. We will begin our study of limits working with relatively basic rational functions like those addressed in section 2.6 of your textbook. Okay, for this type of function, interesting refers to x values at which the graph of the function has a vertical asymptote, a removable discontinuity, otherwise known as a hole, and or at its end behavior. Limits can be found graphically, numerically, and or analytically. Some limit problems can be solved utilizing all three methods. Some only two of the three, or perhaps only one of the three will work. In terms of where we are in the textbook, limits are covered in Chapter 12 of your textbook, along with some other topics that traditionally appear in introductory and calculus classes. We will be using the book at times for the topic, but not following its order. For what we want to accomplish with this particular unit, it's not in our best interest to follow the way the chapter does it. So we're going to be hitting most of what's in the chapter, but bouncing around a little bit. All right, first problem that we're going to be looking at is this guy right here. We have the function 3x squared minus 3 over x squared minus x minus 2, and they're kind enough to provide a graph for us of what this looks like. All right, what we're going to be doing is evaluating these limits, and we're going to be doing it using the three different approaches you could take: graphically, numerically, and analytically. All right, so we do have a graph, so we're going to address that first. How much of this stuff can we answer just by looking at the graph that's provided? So the way we read this is the limit of the function as x approaches 2, and that little exponent up there with the negative sign means coming from the left. So as you trace towards, or from the left rather, towards a positive 2, coming from the left-hand side, going this way, as x gets closer to positive 2, what happens to the y value? Well, that y value is shooting down this way, down to negative infinity. So the limit as we approach 2 coming from the left is negative infinity. Okay, the limit of the function as x approaches 2 coming from the right. So that means as the x value gets closer and closer to 2 coming from the right-hand side, what's the y value doing? So there's our x value of 2. Tracing along our graph coming from the right-hand side, the y value is shooting up to positive infinity. Now the last part is the limit as x approaches 2. So this combines together what we talked about from the first two. If the left-handed limit equals the right-handed limit, then that is the limit for the last part here. If those two guys don't agree, then the limit does not exist, and that's pretty universally abbreviated with DNA. So, one place of interest for this particular rational function is what happens at that vertical asymptote. Okay, the function is undefined at the vertical asymptote. We can't say what's happening to the function in terms of a value there, but we can look at what happens as we get close to it. All right, next point of interest is going to be what happens as x approaches -1, excuse me, which is where we have a hole. So, as we approach -1 coming from the left, we're heading towards the y value of that hole. Well, it seems as though that y value is at 2. As we trace towards -1 coming from the right, we're heading to that same hole, which has a y value of 2. The left-handed limit equals the right-handed limit, therefore the limit at that value exists. It's 2. Excuse me again. Alright, now when it comes to end behavior, the limit as x approaches positive infinity, heading this way, x approaches negative infinity, going the other way, there is only one limit. Approaching negative infinity, I might have just said that backwards. They're in different orders. The negative infinity is heading that way, positive infinity is heading that way. There is only one way to get to negative infinity. That's heading from the right. You can't approach negative infinity from the left. Negative infinity is left can be. So as x heads this way, the y value is getting closer and closer and closer to that horizontal asymptote that appears at 3. As x goes to positive infinity, tracing this way, the graph is heading to that same horizontal asymptote at 3. All right, so we answered all those limit questions simply by examining the graph that was given. So what could we have figured out using the other methods? I'm going to go to analytically next. So if we take this function, factor the top and bottom, cancel out the x plus 1s, it gets us to here. Now we know from stuff that we've already talked about with rational functions that if that x minus 2 doesn't factor out, or cancel out rather, we're going to have a vertical asymptote. So at vertical asymptotes, it's always going to be approaching with this type of function, either up to positive infinity or down to negative infinity. So to answer these questions right here, we know it's going to be positive infinity or negative infinity, but we don't know in which direction. So as I mentioned in that little preview worksheet that we talked about, not every method or approach can work with every single type of question. So we need either a graph or the numerical approach that we're talking about. Based on what we know, we don't know whether it's positive infinity or negative infinity to answer these limit questions. The best we can do is know it's one of those two options for each one of those. Now, analytically, for approaching the whole, one of the things we talked about back when we did our graphing rational function unit was you can find the y coordinate of the whole by plugging an x value into the simplified version. So we know there's a hole because the x plus 1's canceled. That's something that we learned a long time ago. So if we plug that x is equal to -1 into the simplified version, that gives us the y coordinate of the hole, which answers those. So this set of questions right here, we originally found them analytically by looking at where is that hole located. I'm sorry, we found it graphically by looking at where that hole is located. And then we could find it analytically by doing the same thing we did a while ago in terms of plugging it into the simplified version. Alright, as far as these guys go, you can know the end behavior limit questions based on horizontal asymptote rules for this family of functions. One of the things we learned a long time ago, if the degree of the top is the same as the degree of the bottom, you're going to have a horizontal asymptote at the ratio of the lead coefficients. And whether we do the unsimplified or the simplified version, it comes out to that same 3. So for this family of functions, if it has a horizontal asymptote, that's going to be the analytic way of determining the end behavior limit questions, meaning as x approaches negative infinity, as x approaches positive infinity. All right, third approach, numerically. Okay, so for numerical problems, very often you're going to be asked to fill in some kind of table of values. So what I have is I already have my function in y1. That other function in y2 is going to be the second example we do. That's de-highlighted, so it's turned off. If we hit graph, just do a quick confirmation. The graph on the paper here appears to match the graph on my screen, confirming I probably have it typed in correctly. And now what I'm going to do is double check my table set. I want to go to second window. I want Ask Auto, and I'm going to type in x values that will help us answer the limit question. So for this first table that's set up here, we want to see what happens numerically as x approaches 2 from each direction. So as you approach 2 coming from the left, 1.9, 1.99, 1.999 are values that get closer and closer to 2 coming from the left. Coming from the right, x values that get closer and closer to 2.1, 2.01, 2.001. So I'm going to go to my table and I'm going to type some of these values in. So 1.9, 1.99, 1.999. So we don't have these approaching one particular y value. Negative 27, negative 297, negative 2997. They seem to be going down to negative infinity. They didn't ask us to go any further in terms of filling in the table, but if we did, 1.99999, 1.99999, I'll throw an extra 9 in there, I forgot how many I did. And you can see that confirms the fact of as x approaches 2 coming from the left, those numbers are approaching negative infinity. I'm not going to fill those in for the purposes of time, but you typically be asked to fill in that table. All right. Approaching from the other direction, 2.1, 2.01, 2.001. So these y values aren't going towards any one particular value. They're getting increasingly larger. So if we did 2.0001, 2.0001, that confirms the fact of these are just getting bigger and bigger and bigger and bigger. Or the limit as x approaches 2 coming from the right-hand side is going up to positive infinity. If the left-handed limit doesn't equal the right-handed limit, the limit at that value does not exist. All right, the next little table that's set up here is examining what happens as x gets closer to negative 1. Let's delete these out. So approaching negative 1 coming from the left, negative 1.1. Oops. I don't know what I just did. Back to that table. Negative 1.01, negative 1.001. And we can see that the y values appear to be getting closer and closer to 2. I'm going to do a couple more, although we weren't asked for it on the table, just to confirm. So 1, 2, 3 zeros. Now that number 2 appears here. It actually rounded to 2. The actual value is 2 point and then 4 zeros, 333 stuff. So as x approaches negative 1 coming from the left, the y value is getting closer and closer and closer to 2, which is what we had here from looking at the graph. Okay, coming from the other direction, negative 0.9, negative 0.99, negative 0.999, and I'll do one more, negative 0.9999, and we can see the same thing is happening with the y values. the y values are getting increasingly closer to 2. That doesn't actually equal 2, it rounded to 2. So the left-handed limit, as we approach coming from the left, the y value got closer to 2. Approaching from the right, it got closer to 2. Left-handed limit equals right-handed limit, therefore the limit at that value exists, it is that number. Alright, as far as the end behavior goes, as x approaches negative infinity, as x approaches positive infinity. So as x goes to 10, 100, 1,000, 10,000, and we'll do one more just for fun. 1, 2, 3, 4, 5, 6 zeros. We can see that the y values are getting closer and closer and closer to 3. The last number is actually rounding to 3. So as x approaches positive infinity, the y value is getting closer and closer and closer to 3. Okay, negative infinity be negative 10, negative 100, negative 1,000, negative 10,000. We'll do one more, just put a whole bunch of zeros here. And we can see the y values are heading to that same 3. Alright, so wrapping up that first example here, we had our function. With that function, we're given a graph. That's not always the case. Very often you have to create your own. These are the limits you would typically be asked where something interesting is happening. At positive 2, where we have a vertical asymptote, and negative 1, where we have a hole, and then end behavior is usually considered interesting for most functions. We address those graphically, numerically, and analytically, not necessarily in that order. Some limit questions, all three approaches will work. Some limit questions, they don't work so well. So that's why it's important to be able to have a complete toolbox, so to speak, in terms of knowing all three methods, applying which ones work best given the question at hand. All right, we're going to go through another example. So for this example right here, our function is x to the third plus 3x squared plus 2x all over 4x squared plus 4x minus 8. So it appears as though we have a hole at x is equal to negative 2. We have a vertical asymptote at x is equal to 1. So those would be typical places where we'd be looking to see what happens as far as limits go. So get that right there. The first set, as x approaches negative 2 coming from the left, well, there's our x value of negative 2. As we approach coming towards the left, it's heading towards that hole. Okay, that hole doesn't appear to be at a nice clean lattice point. It looks like it's a little bit below the x-axis. So graphically speaking, we know it's less than 0, bigger than like negative 0.5, but the best we could do to fill those in graphically would be to take like a good guess. So we can't really address that graphically other than take a reasonable guess. All right, what about the next set? As x approaches 1 from the left, as x approaches 1 from the right, as x approaches 1 period. So at x is equal to 1, we have that vertical asymptote. So tracing coming from the left, that shoots down to negative infinity. Tracing coming from the right, it shoots up to positive infinity. The left-handed limit does not equal the right-handed limit, therefore the limit at that value does not exist. Okay, end behavior. If we look as x approaches negative infinity, the graph appears to be shooting down in that direction, which means it's not going towards one particular y value, it's heading down to negative infinity. As x approaches positive infinity, the graph is shooting up in that direction, so that's positive infinity. Alright, so that's the best we can do for answering this block of questions graphically. Now, analytically, what approaches would we have? We already have some work done here. If we take this and factor it, first step gets us to there when we take out the GCF. Second step gets us to here after we factor the trinomials. The x plus 2's cancel. That leaves us this right here for our simplified form. So we know, based on the structure of this problem, that we have a vertical asymptote at x is equal to 1, because that is producing restriction that does not cancel out in the end. So analytically, we know that it's going to be positive infinity, negative infinity, some combination to answer these guys right here. Which is which, we can't tell just by this. We would have to either have some graphical or some numerical information. All right, as far as answering the limit questions at -2, we know we have a hole at -2 because those x plus 2's canceled out. So what we can do to get the y coordinate of that hole is to plug the -2 into the simplified version. So after you plug it in and do your order of operations, we get -1/6. So whether we approach from the left or the right, the graph heads to that same hole, which has a y coordinate of -1/6. So unless you have some crazy graph visualization knowledge, you're not going to get -1/6 from looking at that picture. The graphical approach, we can get a rough estimate, excuse me, but we're not going to be able to most likely get that -1/6 number simply by looking at that graph. All right, as far as the end behavior, we know that if the degree of the top is exactly 1 bigger than the degree of the bottom, it has a slant asymptote. We know that we can find slant asymptotes by actually doing a long division. Now, whether you do the long division with the original problem or long division with the simplified version, it's going to give us that same part that we care about as far as the slant asymptote. It's going to be that first set of terms without the remainder. So we know we have a slant asymptote at 1/4 x plus 1/2. Well, that's a linear that rises to the right. So if we know the slant asymptote rises to the right, that tells us the end behavior of the graph. That as we head towards positive infinity, it goes up to positive infinity. As we head towards negative infinity, it goes down to negative infinity. So that's how we would get those two numbers analytically without seeing the graph, by knowing it has a slant asymptote and knowing which direction that slant asymptote heads, whether it's up to the right or down to the right. All right, as far as the numerical approach, let's see how that plays out for this one. So I'm going to go to my graphing calculator, go to y equals, I'll turn off that first function and the second function, hit graph just to make sure that the graphs seem to match up. And they look pretty similar, so I can feel reasonably confident that I have it typed in my calculator correctly. Alright, I'm going to go to my table, get rid of those values I had plugged in there, and the first table here that we're looking at is approaching -2 coming from the left, -2 coming from the right. So -2 coming from the left, values we can use, -2.1, -2.01, -2.001. That's all they asked us for in terms of filling in this little table. Typically, I like to go a little bit further just to confirm it's heading where I think it's going to go. So -2 point, 3 zeros, and then -2.4 zeros, 1, and that decimal of -1.66666. Well, if that was 6 repeating all the way across, we would know reasonably for sure that that would be the decimal approximation for -1/6. In this case here, you may or may not recognize it. You can probably get a limit answer that's very close to -1/6, but you might not have that -1/6 exact. And that's just one of the drawbacks of, if you're taking a numerical approach, you may get a close answer, but it may not be the exact answer, especially if that exact answer is in terms of pi or it's a radical expression, which is typically going to happen when we get into the trig versions of these guys. All right, next table here we're looking numerically as we approach positive 1 coming from the left, as we approach positive 1 coming from the right. So let's, we did not finish up the coming from the other direction. I apologize. Finishing up the first table, coming from the right-hand side for that first set would be negative 1.9, negative 1.99, negative 1.999, negative 1.9999, do 4 nines, and then 5 nines. And the same story in terms of you may or may not get that negative 1/6 as the limit approaching from the right-hand side. You might have to go a little bit further. Well, you definitely have to go a little bit further to get that repeating 6 all the way across the board. Same limitations we talked about. All right. Now on to the second table. That's approaching 1 coming from the left. Too many decimal points there. So the y value isn't going towards one particular number. It appears as though it's going down to negative infinity. So that confirms, where is that up top? This one here, I believe. This approaches positive 1 coming from the right-hand side. So 1.1. That's 1 point again. 1.01, 1.001, 1.00, just do a whole bunch of zeros, 1. And we can see the y values aren't going to one particular number. They're shooting up to positive infinity, which corresponds to this right here. So approaching negative 1 coming from the left is going down to negative infinity. Sorry, approaching 1 from the left is going to negative infinity. Approaching 1 from the right is going to positive infinity. The left-hand limit does not equal the right-hand limit. Therefore, the limit at that value does not exist. All right, lastly, the end behavior. We'll do the positive infinity first, 10, 100, 1,000. I'll put a whole bunch of zeros. And we can see the y value does not head towards one particular value. It's shooting up to positive infinity, which corresponds to this guy right here. The limit as x approaches positive infinity of the function is positive infinity. And behavior is upright. All right, last part. That's this table down here. This is examining as x goes to negative infinity. So negative 10, negative 100, negative 1,000, and put a whole bunch of zeros. And we can see the y value does not head to any one particular number. It's shooting down to negative infinity, which corresponds to this guy right here. The limit of the function as x approaches negative infinity is negative infinity, where the end behavior is down left. And that wraps it up for day 1 of an introduction to limits, working with some basic rational expressions we've seen before. As we go on through this particular topic, we will look at different types of functions, different types of functions other than rational functions, mixing in trigs, logs, exponents, all the different things we've examined. And we will be looking at some more sophisticated types of strategies to get the analytic answer. It's not going to be the full-fledged what you'll see in calculus. As I mentioned in the overview, this isn't supposed to replace Chapter 1 of calculus, just get you prepared for it with the basic ideas and concepts.